Hi everyone. Today what we're going to work through, you see the title at the top, we're going to go through a complete review of solving systems. Now, I do want to clarify a little bit when I use the term review, that the concept of solving a system should be complete review. However, I am going to argue that I think you're okay if you haven't really had experience with everything that we covered today. That kind of depending on the way you got here, your background in your high school math, we may have differing experiences with how much we've solved these particular systems. So I'm going to call it review because there's technically not going to be one thing that is new in what we covered today. However, I just don't want you to be alarmed. If as you're going through a particular problem, you're saying to yourself, I've never worked with something like this before. No worries. It doesn't mean you're behind. It just might mean that, you know what, like we haven't seen this context with something. So as we progress, I'm going to ask you, rely back on your old stuff, your skills that you have. You actually have everything you need for today. So let's take a look at problem one. I'd like you to go through and solve that system. We've reviewed this already this year. I should be good to let you pause the video and you work your way through to a final solution. Okay, pause it now. Okay, we are back. So I think the big part for us as we progress through is more, how did you solve it? And then for me to address a little bit of formatting, some communication. So the first thing that everyone should have done is we need to label our equations. We have our equations labeled. They have circles around them. That is our universal mode for that's what it means to represent an equation. So I now have equation 1 and equation 2, and you have two options as to how you want to solve this. This would not be my particular mode to solve. However, I'm going to suggest or guess that most of you would have solved it this way. That you maybe would have taken equation 2, since we are so used to writing equations with the y isolated, and I can easily isolate that second equation. Now, I'm going to just change the color of that because I want that to be in a different color. So maybe I take that second equation and, as I said, I rearrange it. Whether I wrote 6 minus 2x or negative 2x plus 6 doesn't really matter, because now that I have isolated that, I am going to sub equation 2 into equation 1. Now, before we go further, I need to be very clear that you don't have to match up with my solution. That is, you didn't have to take equation 2. Maybe you take equation 1 and you rearranged it and got the x all by itself. Then you would have subbed 1 into 2. Perhaps you didn't even use substitution as a method and instead you used elimination as a method. So by no means do you have to have the same solution as me, but we do have to match up in the end. So I'm going to continue on just going through and subbing 2 into 1. So I'm going to copy out equation 1, and wherever I see my y, I know that I can replace that with my negative 2x plus 6. Okay, I started off, I had a problem. I had two equations with two unknowns. I couldn't solve that, but now in my blue, I have one equation with one unknown. I can solve that. The rest here just becomes mechanics. Expand in your 3. I get a negative 5x is going to equal negative 6, and I get x being 6/5. So hopefully not too bad. Now I can take that x value and I can sub my x equals 6/5 back into one of my original equations. For me, I think I would sub it back into equation 2, but I could totally run over to the argument of subbing it into equation 1. Like equation 1 just has an x, so I could replace that right away. For me, I'm going to go through and sub it into 2 because my intent is to solve for y. And so when I replace that, all I have to do is isolate my y. I don't have to get rid of any coefficient. So that means that I have a 12/5. Okay, now when I go to get my y all by itself, I think I should be good to be able to get rid of that 12/5. That means I'm going to have to subtract 12/5. But that means I'm going to also need a common denominator with the 6. So I'm just going to get rid of that green, and we should be good that my 6 in fifths is going to become a 30. I now need to subtract my 12, and that's all with my common denominator of 5. Of course, you can see there's your 30 divided by 5, which is 6. And then we have our minus 12/5 as we're isolating. Okay, I can clean it up. There's my 18/5, and I have now solved my system. The only thing left to do is to actually state my solution. So I state my values always in alphabetical order, and there we go. So hopefully we got down to that same thing, and as I mentioned earlier, maybe we got there different ways. Okay, we could have used substitution, could have used elimination, we could have eliminated a different variable, we could have used substitution in a different way. But let's make sure that we get down to 6/5 and 18/5 as our two solutions. I now need you to look back at everything that is in orange on that screen, because I require all of that within my solution. There is your proper communication. We need to make sure that we are good with all of that communication in our solution. Okay, now just for a little bit of context, I want to jump and take a look at a graph. So let's take that system and let's just graph it. Okay, so I just hopped onto Desmos to save us some time. You can see on the left side, there is my system, my two equations. And I just wanted to pull up a picture to remind us of a key thing. Remember that every time we solve a system, we are finding when one equation exists in the same position as the other equation. That is, what variable values satisfy both equations at the same time. So really all we're finding then is a point of intersection. And so if I hop onto Desmos and I just select that point, you're going to notice there is our solution. Now, Desmos represents it as decimals, but you'll notice if you do a quick conversion, your 1.2 is 6/5, and your 3.6 is going to be 18/5. There is our point of intersection. So the other thing to keep in mind is when we give you the instruction to write your solution in alphabetical order, we're actually writing our solution as a point of intersection. I don't know how often you think about the fact that X and Y is in alphabetical order. Okay, hopefully that just gives us a full context, and we should be good to jump in to solve some more systems. So I want you to take a look. I've put up a system here, and before you copy it down, I just want you to notice it's the exact same system that we just finished dealing with. So I could call this problem A. But what I need to make sure that we're good with is we've now just done a quick review, not that it should have been needed, but we recognize that both of those equations are linear. Like we notice that they're both degree 1. If I was to isolate my y, then the exponents on both my y and my x are 1 in each, therefore they represent lines. That I would hope that unless the equations really presented themselves to where it was really, really easy to use substitution, that your default method would actually be elimination. Now, the reason I say that is in preparation for advanced functions next year. You're going to get to the point where you're not solving two equations, two unknowns, or you're doing that so often, but that's like as easy as it could be. That's background knowledge. You're going to get to the point where you're solving 5 equations and 5 unknowns. So like you'll have an equation that's like a plus 2b minus 3c plus 4d minus e equals 0. And then you'll have another equation with all those things equals 5. And then you'll have like a 2a plus 3b minus... And you're going to have 5 equations with 5 unknowns. And if your default method every time you have a linear system is to go through and use substitution, it is going to be very difficult to solve these systems. Let alone, it's probably going to take you 3 pages to solve something that should take 1 page. So I want to make sure for anybody whose knee-jerk reaction, their default method, I like to say you're a substitution junkie. If substitution is the only thing you do or the predominant thing you do, then I want to make sure we're good with elimination. I'd like us to get down a solution for elimination. So I'm just going to get rid of a little bit of that arrow, and let's make sure that we have a solution for it. So nothing would change in terms of my equation 1 and equation 2. I should be able to get rid of the fact that they're linear. We can identify that. Right now, I cannot eliminate either one of those variables. If I was to add or subtract those two equations together, I don't eliminate an x or a y because they don't have the same coefficient. But let's say that I viewed that as I'm going to multiply equation 1 by 2, because that would now generate the equation 2x plus 6y equals 24. Now I notice my x terms between my equation 2 and my new equation have the same coefficient. I can eliminate my x's. So a couple things in terms of formatting. I just unsimplified an equation. That means I have a new equation, so it becomes equation 3. And between equation 2 and equation 3, I can now eliminate my x. If I took equation 3 and I subtracted equation 2 from it, I would eliminate my x's. Now, for some of us in the past, we have written this down. Maybe we would have copied out an equation, perhaps. There's my equation 2. And now you want to tell me to subtract those, and you go and do something like this. You're going to lose communication marks on that. Because we have to be very careful. It's not like the positioning of the negative. It's the fact that all you've done is just slide a negative in there. I'm going to just clean up that equation for a second. Because even if I did this, I think it's important for us to see that that negative only applies to that first term. That you'd almost have to put brackets around the whole thing. And why are we putting brackets over something that crosses an equal sign? That the way you should properly express the fact that you are subtracting those two equations is through that statement right there. I am taking equation 3 and I am subtracting equation 2. So if you want to copy stuff out for comfort, you can. I just wouldn't. Sometimes you guys copy down stuff and you make a silly little mistake. Right now, we should be able to calculate 3 subtract 2. So that is now going to give me a 2x minus 2x. Those cancel out perfect. 6y minus 6y minus 1y is 5y. And 24 minus 6, there's my 18. Now I create a very simple equation I can solve. There's my y equals. I can now sub my y value back into one of my originals, and maybe I sub that into, I don't know, like let me sub that into 2 in this case. It'll see something a little different. That means that I get a 2x plus 18/5 is going to equal 6. And now I have a little bit less work in that I don't have to multiply a coefficient in, but I'm going to take 6/5, so there's 30 of them, minus my 18. That gets me down to 12/5. Now I have an option here. I'm going to divide out my 2. When I divide out the 2, this is about as long as I could make it. That means that my x would be 12/5 divided by 2. Well, to divide fractions means I flip and multiply. That means that I have my 12/10 and reduces to 6/5. I think that's a lot of work, and we should be good to jump over an awful lot of that. So as we work our way through and we try to get rid of that 2, we should be quite comfortable that to get rid of a times by 2, I divide by 2, and any time that I am dividing a fraction by a whole number, I multiply the bottom by it. Of course, you can see why that's the case because we multiply by the reciprocal. So I think to jump straight to the blue and say that that's going to be 12/10 isn't a bad thing, and now you can reduce the fraction. Or I would say we're really showing a lot of maturity if in our minds we can already see that since I'm going to have the factor of 2 on the bottom, I can divide that out right away. And we can come straight to x is going to equal 12 divided by 2, which is 6/6. State your point of intersection or state your solutions in alphabetical order, any way you want to think about it, and there you go. So a little bit of review of what a system being solved by elimination should look like in a solution. Okay, we should be good with that. Now let's jump into something a little bit different. Okay, I'd like you to take a look at C. C is going to look a little bit different to you, and I actually want you guys to start this one off on your own. Now, I'll be honest with you. Okay, so equation 1 and equation 2, that was not the start I was talking about. Yes, we are going to label our equations with their numbers. There's their name. Now what I want you to do is I want you to go through and solve this. However, I want to take this in its bits. For some of you, this might be the first time where you've ever been asked to solve something specific to what C is. Again, as I said at the beginning, this should all be background knowledge, but it doesn't mean that we're going to feel the same way in terms of comfort about every problem. So what I want to do is do it in its bits. And right now, all I'd like you to do, I'd like you to write down your first line. I want you to make a decision as to what you want to try for this problem, and then take that one action. Don't go any farther. That is, don't write down the next line. If we make a bad decision, I don't want you guys to go too far in the wrong direction. So all we're going to do, first decision. Come up with a plan, take that one action, and stop. Okay, pause the video now. Okay, hopefully we've made a decision and we've got something down. Now, I want to talk about a couple of those decisions, or specifically, I want to talk about one of those decisions. And I need you guys to understand why it's really costly if we make this decision. If I was going to call this like a 4-mark question, you might get like 0.5 or 1 out of 4 if you make this one mistake at the very beginning. So I want to make sure that we understand how important it is that we don't make this mistake. Okay, I could totally see some people, and history would say that I've got some people who are going to look at that and say, okay, well, Gray, you just talked about elimination being important. And so if I want to use elimination, I'd really like to get rid of the squares on equation 2. And I notice that each one of those terms is a perfect square. So I'm going to take the square root of every one of those terms, and I'm going to create the equation x plus y equals 5. That becomes equation 3. And now between 1 and 3, I could use elimination, and I could solve my system. Okay, that's my one step. And I need you to know that the mistake you made there to get to that blue equation was so significant, it drastically changes the problem. Okay, I'm going to bet and say I've got a bunch of people who have that blue equation. So first off, I want to talk about why we can't do that, where the mistake was in there. Okay, first off, let me just get rid of that blue arrow. And I want you to take a look at the first two equations I gave you, equation 1 and equation 2. And I want you to imagine what shapes those would be if we were to go through and graph them. We should be good that the first one, there's my good old line. I rearrange it, I get y equals x minus 1, good old line. My second one, I'm hoping that you can remember from grade 10, that's my good old circle. Maybe you even remember specifically, that's a circle with center 0, 0 and radius 5. Okay, so now I have to ask you the question. If what you did to build the equation 3 was justified, some of you guys even put the word in legal, you were allowed to do it, That is, if I simplified equation 2, to turn it into equation 3, then I have to ask you, how did you change a circle into a line? Because that's what equation 3 is. There's my degree 1, y equals negative x plus 5. So clearly, doing what we did to equation 2 to get equation 3, that idea of taking the square root of every term, was an error. Okay, so we can see it from a graphical standpoint, but maybe we can't see it from an algebraic one. So what I want to do is I maybe want to hop off and just kind of take a look and see about your square root decision. There is nothing wrong with us taking equation 2 and saying, I'm going to take the square root of both of the sides of my equation. There is nothing wrong with that. Where our error comes in is that we think that that green that we just wrote down, which is 100% correct, is somehow equal to this. Now, we talked in past units about how we deal with that radical operation. And the fact that there are hidden brackets underneath that mandate that we would have to do that addition before we do the root. So I don't need to revisit that theory. I just very quickly want to say we're all good that the right side is 5. The left side is the one that we can kind of have a little bit of a hiccup on. So if I just slid, I don't know why I wrote root 5. How about just 5? So if I just created another problem and I said, hey, would we all agree that 9 plus 16 is equal to 25? So if I took the square root of 9 plus 16, then that should equal the square root of 25. Well, the square root of 25 is 5. We can calculate that just as we did above. And clearly, when I take the square root of 9 plus 16, I need to take the square root of 9 and the square root of 16. And obviously, this is wrong because it's not equal to 7. So remember your hidden brackets. Don't mistake the square root of multiple terms with the square root of one term. Let alone, I would come back to you and I would say, why is Pythagorean theorem what it is? We've talked about this before. If me taking the square root of both sides of an equation is just me taking the square root of individual terms, then why isn't Pythagorean theorem not just a plus b equals c? That's much easier. So I hope we can see then our error in us taking the square root of individual terms. So I'm going to get rid of everything on there. And for anybody who took that first step of taking the square root of equation 2, I'm hoping I have demotivated you from doing that. Okay, so how should we go through and solve this one? Well, this is something extra that I think we should talk about. Notice that your equation 1 and equation 2 are different degrees. We already talked. It's linear. That one is a circle. And if I have relations that are different degrees, then I want to use substitution. It doesn't mean that it's an always case, but I'm going to argue if you wanted a default method, I think that's your best case. If it's linear throughout, then use elimination. But if I have different degrees, I'm going to use substitution. So that means that I'm going to take equation 1 and I'm going to rearrange it. So I'm going to do my solution in green. So maybe I take that equation 1 and I just get my x all by itself. Just for a little variety in case anybody felt like you always had to get your y all by itself. Okay, I do that. I can now sub equation 1 into equation 2. So wherever I see the x, I can replace it with y plus 1. And I now have equation 2, and it's all in one variable, and I'm good to go. So what I'd like you to do right now then is work your way through, and I'd like you to solve the rest of that system, or at least let's solve for y. Okay, pause the video now, give it a shot. Okay, we're back. So the next mistake that you may make, I need to make sure you don't make it. I'm going to bet and say that I have a bunch of people who have that on their page. And so they got a 2y squared equals 24 and a y squared equals 12 and so on and so on. I'm hoping you can see that we have to slow down and make sure that when we expand that first bracket, that we get our trinomial. Okay. Now I come in on that. That will have a significant difference in the equation that I have to deal with. Okay, I noticed pretty quickly that I can't collect my y's into one variable term, so I'm going to get everything on one side, put it in standard form. Now, I'm also noticed that I have a common factor of 2 in every single one of my terms. So let's divide out that common factor of 2, and let's shrink that equation down to that. That's going to allow me to work with smaller numbers, and especially in this case, that's going to allow me to have to factor a simple trinomial instead of a complex one. And we come in on 2 possible values for y. Okay, now I'm going to give you something in terms of an organization structure that I think will be very useful. As you work your way through, this is going to be the really sort of a really common problem that you're going to face in a slightly different context if you happen to be on the pathway to take calculus. That there's going to be a lot of times where we solve for systems that have multiple points of intersection. My suggestion to you is, now that we're about to write our next communication statement, almost build up a chart. So what I might do is I'm going to say, I'm going to sub y equals -4 back into one of my originals. And right beside it, I'm going to write sub y equals 3 back into one of my originals. Okay, we also now come to a point where I need to maybe kind of rework some wording that you heard quite a bit in grade 10. Almost to the point where we've like defaulted it. That you probably were told, and now take your y value and sub it back into one of your original equations. And at some point the question was asked, does it matter? And you probably heard, no, it doesn't matter. Sub it into either one. Okay, I need us to see that it does matter. I'm not changing your theory in a way. It's just that what you were exposed to in grade 10 was always linear systems. And it doesn't matter in linear systems. We'll talk why. But in this system, it will absolutely matter. So I don't want you to copy this next part down. Do not. I'm going to take that y value and I'm going to sub it into equation 2. So I'm going to sub y equals -4 into equation 2. When I get that, I'm going to now have this equation, of which I can solve for x, get rid of your 16, and when I take the square root of 9, I get 2 answers of +3 and -3. What that tells me then is I have 2 points of intersection, +3, -4, and -3, -4. That's what that tells me. Now, what I want to do is I want to hop out of this for a second. And what we're going to do is we're going to actually take a look at the picture of this graph. Okay, so I've just hopped onto Desmos again. And you'll notice that what I've done is I've gone through and I've graphed our system. And what we see is our blue circle, centered 0, 0, radius 5, and we see our red line. Now, I went through and I've also plotted both the points that represented the points of intersection that we just found by subbing our y value back into equation 2. Okay. What we confirm then is, yes, those 2 points, those green points, both exist on the circle. By subbing in your y value, you just found the x values that have a y value of -4. And so we found that we have 2 points. -3, -4, +3, -4. However, when we go through to solve the system, we are looking for the point of intersection. And the problem that arose by subbing that into equation 2 was that, well, I can have points that could be above each other, across from each other on a circle. That is, one y value could give me different x values. They may not represent the point of intersection. You can see it on your picture. You can actually see which one we needed for the problem. The actual point of intersection is at -3, -4. That point 3, -4 should have never been part of our solution. However, algebraically, it's going to always pop up. So I want to hop back into our solution now that we can see our picture so that we can see the approach we need to take, but now we also understand why we can't just blindly substitute into an equation. So if we go back to that solution now, we can see that this decision to go through and sub into equation 2 caused us a problem. So I'm going to get rid of all of that solution. And we should now see that the best equation to sub in, and in fact, the equation that we should recognize in this case is, I want to sub it back into the linear equation. If it's a line, then I don't have to worry about having points across from each other, points above each other. I don't have to worry about not getting the point of intersection and finding some other erroneous point. So there is what my next step would be to be able to come up with the matching x value. Now when I sub into equation 1, I get my matching x value, which is the only x value that would represent a point of intersection. The other nice part, it also means that I got to work with easier numbers. Like, for me to go through and solve equation 1 or isolate x in equation 1 is going to be easier. Okay, I could do that same thing now if I go and sub 3 back in for y into equation 1. And now, why do I like setting it up this way? It's because when I go to write my points of intersection now, I've got everything columned up. Like, that is, I'm not taking this x and trying to look across my page and match it up with another y and so on. Everything is nice and easy to interpret. I can see there are my matching values, my coordinating values. So I take a look. My first solution then would say the x value of -3 comes with a y value of -4. My x value of 4 comes with a y value of 3. Now I've solved for my 2 points of intersection. And if you think back to the picture, we could see our 2 points of intersection. So, nice. Okay, for some of us, that was the first time that we've gone through and ever solved a system of different degrees. I just want you to take a look at your whole solution and recognize that is all background stuff. For you to be able to take one equation, sub it into the other, that's substitution, that's grade 10. For you to go through and solve that big green equation, that's a quadratic equation from grade 10. And for us to sub back in and solve values, that would be grade 9. So when I mentioned that it was review, it is all review, but we're just really putting everything together. Okay, let's jump in and play with another one. Okay, I want to start you off on D, because I think that I would have a number of people who would struggle with D. And really, it's just a minor issue, and it's us just being comfortable with our function notation. So you've been asked to solve the system between f of x and g of x. And we may look at that and we may go like, but I don't even know where to begin, because like in equation 1 and equation 2, yeah, they both have x's, but one's got an f of x, one's got a g of x. They don't have the same variables. Well, I would say to you, would you be fine if they had x's and y's? Because remember that I can always replace my f of x with a generic output, right? All f of x is the output of the f function. Remember, y equals f of x, so replace it. Same thing in the second one. My output equals 6x minus 1. If I were to graph both of those functions on the same set of axes, they would both have y coordinates. So if you happen to see your system that's presented to you with function notation, know that we can just do that at the very beginning, and you are good to go. Now, you don't have to show me that as part of your solution. You could just jump in and make the assumption that they are y's. Okay, I'm going to get rid of that part, and now I'd like you to finish off that problem on your own. Okay, go ahead, give it a shot. Pause the video now. Okay, we're back. So, in this instance, you could have used substitution or elimination. If you notice, if you took equation 1 and subtracted equation 2, you're good. I don't think I would recommend it because that's going to give me a y minus y, which cancels out, which was the whole point of subtracting them. But on the right side, we have to be really focused that what we have is negative 2x squared minus 5x plus 20, my equation 1, subtract all of equation 2. And a real common mistake is going to be to forget to subtract all parts of it. So I can avoid that risk for mistake if I don't use elimination. So as I mentioned earlier, my equations are of different degrees. And my recommendation to you would be substitution. I think I'm just going to, oops, I need that to be in gold. I am going to sub equation 2 into equation 1. Or sub 1 into equation 2. They both have y isolated. That's going to create this equation. And now you have one equation with just your x's, you're good to go. So we should be pretty quick to be able to solve that one. I think I want to deal with positive x terms, so I'm going to picture everything here going to the left. That's going to give me a positive 11x and a negative 21. I can't collect my x's, so I'm going to look to try to factor it. Two numbers to multiply, that's going to be a 7 and a 3, and that'll give me a 14 and a 3 that I can get 11. And so pretty quickly then, I can see that that will factor, and I can find my points of intersection at 3/2 and negative 7. Okay, if we struggled to get to that point, I'm going to give you an opportunity to pause it and finish off the problem. Okay, go ahead and pause it now. Okay, we're back. So I should see, if I was to look, or have the ability, I guess, to look and see on everyone's page, that we are going to sub x equals 3/2 into equation 2, our line, and we are going to sub x equals negative 7 into equation 2. Hopefully we have all of that columned up, and now it's just a matter of doing a little bit of calculating. So in that case, I now have my 6 times my 3/2. I can see that that's going to reduce pretty quickly. That gets me a 9 minus 1, and there's my 8. And so one of my points of intersection is going to be at 3/2, 8. And my other is going to be my y equals 6 times negative 42 minus 1 more, negative 43. So negative 7, negative 43. Nice, we like that. Now, the only other part that I want to address is some formatting. And this is something that, depending on your comfort level again, this can help you just to shorten up a little bit of your writing. See that big arrow that I drew to go from the bottom all the way up? Well, we don't really have to write out sub x equals 3 halves in 2, because one of the things that maybe frustrated you at the beginning, this function notation where you're like, why would you even bother? It actually comes in a little more useful here. Really, all you'd have to write is g of 3 halves, because you can allow the function notation to speak for itself. That tells you that you're subbing 3 halves into g wherever you see the x. And over on the other side, we could write g of negative 7, and we can avoid writing out all that orange. So just something to maybe speed up your process in terms of communication. Something that you should know you have available to use. Okay, we got one last problem. Okay, so we see problem 2, and I'm going to tell you that I think we got a bit of a doozy again. So this one would fall into that problem-solving category, and one where we really want to kind of stumble our way through. So problem 2, determine the value of k such that g of x, which is equal to 3x plus k, intersects f of x, which is 2x squared minus 5x plus 3, at exactly 1 point. Okay, there's your problem. Determine the value of k so that g of x intersects f of x at 1 point and 1 point only. Okay, same thing as before. I'm going to leave this one with you, and I think that you should be stumbling your way through it. So we should have some practice from the previous day. You might be jumping in and doing some generic kind of mechanical practice that you want to be able to drill down solving a system with little difficulty. All the algebra. Or you said, you know what, I'm pretty solid with that stuff right now. I think I'm going to spend some time playing through on this problem-solving problem. You're good to be revisiting this over the course of the next couple days to be able to knock out some of that problem-solving. Give it a go. Don't get frustrated and give up and look at a solution. Stumble your way through. Okay? However you choose to spend your time, make it worthwhile to you. Best of luck.